Hello, another video on compositional functions today. Let's jump right to it. Okay, all right, so what does it mean to compose a function? So composition is a way to build a new function from two functions. So if we have a function from A to B, and then another function from B to C, so the important thing here is not the name of the range and domains, but the range of what's going to be the inner function has to match the domain of the outer function. Then we can make what's called the composition of G with F. And what we do is we just plug in the inner function inside of the outer function. And then we have a new function from the domain of the inner function to the range of the outer function. Okay, and this is quite a bit to write. So usually it's the shorthand notation is instead of putting the inner function inside of parentheses, you put open circle between the two functions. But the notation is a little bit, it might be a little bit tricky or needs getting used to because when you write G of F, you apply the function to the right first and then the function to the left next. So you kind of move from right to left when you write down functions. So let's look at an example. So let's say F is a sine function from real numbers to real numbers. And then G is some particular quadratic function. So if you want to do G of F of X, you plug in the sine into the input of the outer function G. So we get sine squared plus sine X plus 1. You get a different function if you flip the order of this. So if you put the quadratic function inside of the sine function, so f of g of x will give you something like this. So they certainly look different, but you can kind of tell that they have to be a different function, maybe by plugging in pi over 4 into g of f. Then sine of pi over 4 is 1 over root 2. And you might realize that, oh, this is some positive number plus 1. So this thing is strictly greater than 1. But f of g, this guy, sine function is always between -1 and 1. So it cannot possibly be the same as the function that's described here. So, so we have a new type of operation. So if you have two functions, we could use this open circle composition operator to come up with a new function. But this is not a commutative operation. So G of F is something different than F of G. So that's important to know. Okay, so let's prove some facts about compositions. Here's 3 facts that you should know. If you have composition of 2 injective functions, then the composition is going to be injection. The composition of 2 surjection is going to be a surjective function. And then if you combine those 2 together, you get the composition of 2 bijection has to be a bijection. And furthermore, you could actually write down the function, the inverse function in terms of the inverse of the 2 function that's involved. The inverse of G of F is going to be inverse of F composed with inverse of G. So you kind of switch the order of the inner and the outer function when you do the inverse. Now, I'm not gonna prove all three of these. I'm just gonna prove one of them, but I do want you to try to prove all three. So I think in the previous video, I proved something about injective function. So maybe I'll prove the part B here. And I hope you take the time to try out and see if you can prove the part A as well. Okay, let's look at the definitions we need. All right, so we're using competition of two surjection as a surjection. So we need a definition for surjection. And we're actually going to end up using this definition 3 times, right? So definition for the surjection for the two function that's involved, that's composed, and we also have to use the definition of the surjection for the composition itself. So we're going to use it 3 times. Function is a surjection if for all b in the output, there exists a such that f of a is equal to that number b. Okay. All right, so let's prove it. Okay, so let's say f and g are surjections. What we want to do is prove that the composition is a surjection. So to show that it's a surjection, what I have to do is I have to look at any number in the output in the range C, and then show that there's at least one number that maps to that. So that's the goal. So let's start with any C in the range of the composition. Now what I'm going to do is I'm going to use the fact that the outer function is a surjection because it has the same range, right? If you have any C in the target, there exists B in the domain such that G of B is equal to C. So we have that because G is a surjection. Okay. All right. Furthermore, I have this B here. For any B, there exists an A such that f of A equals to B because F is a surjection. Okay. So now I have this A, but if you kind of unwind the definition, if you plug it into the composition, well, f of A is equal to B. So I can replace that. And G of B is the same thing as C because of this statement here. So C in the beginning was arbitrary. It was any C. And I was able to come up with A that maps to that. So G of F is a surjection. I hope that made sense. Okay. Another fact about proposition on compositions. So we learned that composition is not commutative. I cannot switch the order, but it turns out that you can change the parentheses. So it's associative. It doesn't matter which composition you process first. Precise statement is as follows. If f and g and h are 3 functions so that they compose, h of g of f or h of g of f means exactly the same thing. Let's unwind the definition to just check, okay? So I'm gonna start with the left-hand side and I'm gonna end with the right-hand side here. So h of g of f is what I wanna start with. So this composition on the outside means I'm gonna put the inner function g of f inside of the outer function h. So that's what goes there. So that's equal to that by the definition of the composition. And now let's look at the composition on the inside. So g of f means f function is sitting inside of g. So that's what goes there. But just kind of ignoring this f of x for now, g is followed by h in plugging it in. So that's the same thing as the composition. So I could use the definition of the composition, and that's what you're applying to the number f of x. But this is the same thing as applying f followed by h of g. So that's what that means. And just by unwinding the definition, with a chain of equalities, we just showed that the two sets of compositions are equal to each other. So once we know this, we know that it's associative, we can drop the parentheses and say, well, we just have three functions, h of g of f. As long as the order is respected, the parentheses of how we group the composition together does not matter in the long run. Okay, I hope that made sense. I will see you next week.